In this video, I'll go over how to do the calculations for a enthalpy reaction for experiment 8 Hess's law. So I'm just going to do one trial, and the other trial you'll follow the same way. Don't forget you got to average your two trials. So this is data that I took. Your data may look very different than mine, which is okay. Remember, we're monitoring the temperature change. So this reaction, NH4Cl, ammonium chloride with sodium hydroxide, this is the equation that we get when we do that. Where did I get that? It's actually on page 1 of your handout. So here's the equation for reaction 3, and our task is to get the enthalpy of this reaction, measuring the temperature increase. So this is the data that I got. I got a change in temperature of kind of small for this reaction, 0.480 degrees C. And from that, we're going to calculate all the different heats, lowercase q, in that. So to figure out the heat of the solution, it's going to be the mass of the solution. So the mass of the solution here is 40.60 grams. I got that 40.60 grams by taking the mass of the solution and the calorimeter apparatus and just subtracting the mass of the calorimeter apparatus alone. So subtracting that gets the mass of the solution and the cup. Now to just get the mass of the solution, you're going to take the mass of the solution with the calorimeter cup, subtracting it from the calorimeter cup by itself. So doing that, I'm getting a mass of the solution of about 40.60 grams. The specific heat, we're going to use the specific heat of water. Now, if you look here, the specific heat of water, they tell us this in our lab handout. The specific heat of water is going to be 4.184 joules over grams degrees C times the change in temperature, and that's boxed in blue here, 0.480 degrees C. So when I added the NH4Cl to the NaOH, it only went up to 0.48 degrees, a very small hike in temperature, if any at all. So the grams cancel, the degrees C cancel. I'm getting a heat of solution of, circle at 81.54 joules. All right, now don't forget, for those of you that did the lab, when you do this reaction, not only is there heat that's released, but there's also heat released to the actual calorimeter apparatus. That's the styrofoam cups and the container in which the styrofoam cup is housed in. And Qcal is going to be C times delta T. Now this C here is what we're going to call our heat capacity. Okay, the C here is our heat capacity, and that's given to us as a constant. Remember, specific heat and heat capacities are constant, and that's going to be 10 joules over degrees C. So here we have 10 joules over degrees C. Remember, that's a constant, times our temperature change, and our temperature changed really slightly, 0.48 degrees C in our third reaction. You'll notice in your first and second reaction, they really shot up rapidly. And that's 4.80 joules. So that's how we get the heat of the calorimeter. The heat of the system, which is really what we're interested in, the actual reaction between ammonium chloride and NaOH, is actually going to be minus Q solution minus Q cal. Okay, so this is given to us in our laboratory handout. So minus Q cal minus Q solution. So that's going to be minus Q cal is minus 4.80 joules plus a minus 81.54 joules, and we get, adding those two negative numbers together, we get about minus 86.34 joules. Okay, so that's the heat of the actual reaction. Notice the minus sign tells you it's all exothermic, but that's just for the reaction. If we want it per mole, now they want it in kilojoules per mole. That's the customary standard. So we're going to convert this to kilojoules. So we're calculating it in kilojoules per mole. So we're going to convert that to kilojoules, move the decimal places 3 places to the left, per mole. Now the thing here is per mole of what? It really doesn't matter per mole because it's all 0.04 moles. Okay, so you can see here we reacted 20 milliliters of 2 molar. And it's all the same concentration, 20 mils, 20 mils, 20 mils. same volume. So all of it's going to be 0.04 moles. So whether it's per mole of NH3 or per mole of ammonium chloride or per mole of NaOH, it doesn't matter. It's always going to be 0.04 moles. So we're going to take this kilojoules and divide it by 0.04 moles, and we'll get our final answer. And I'm going to box it here of minus 2.2 kilojoules per mole. So utilizing that same rationale, we're going to do that for trial 2 and then get an average. So the average here that I got is minus 3 kilojoules per mole. The literature value according to post-lab question 2B is minus 3.9 kilojoules per mole. So this is from the textbook. We got experimentally minus 3 kilojoules per mole. That's pretty good experimentally with what matches to what is considered to be the correct value.